The blending of incompatible crudes will often change the ratio of the sera molecules. This may ultimately result in asphaltene instability. For example, the mixing of more asphaltenic crudes with more paraffinic crudes such as light tight oils. Research has shown that the total quantity of asphaltenes also has a direct effect on the severity of asphaltene fouling. As a result of crude incompatibility, asphaltene instability may occur. Asphaltene instability has been attributed to numerous issues in the refinery, including decreased energy efficiency, increased carbon dioxide emissions, a higher frequency where heat exchangers need to be cleaned, and increased crude throughput. In order to prevent these problems, it is important to know the chemistry and structure of asphaltenes. The asphaltene fraction is currently defined as the oil fraction that is soluble in aromatics but insoluble in paraffins. Typically, the asphaltene fraction is identified using its solubility in toluene and insolubility in N-heptane. However, as more research is done in determining the structure of asphaltenes, this standard may change. The asphaltene composition is influenced by multiple factors, including the choice of solvent, contact time, and solvent-to-oil ratio. The exact structure of asphaltenes, however, is still a subject of debate. Further complicating matters is asphaltene composition being crude-specific. The chart on the screen shows the elemental composition of the asphaltene fractions obtained using N-heptane for 7 different crudes. One can see that the elemental composition varies significantly among these crudes. The ranges for the elements on a weight % basis are: carbon from 78.4 to 87.2, hydrogen from 7.0 to 7.6, oxygen from 0.6 to 4.6, nitrogen from 0.9 to 1.6, and sulfur from 3.5 to 9.8. As mentioned previously, there is still no consensus on the structure of asphaltenes. In fact, there are different models with evidence to support each. The two most prevalent are the paracondensed model and the archipelago model. The paracondensed or island or continental model described asphaltenes as large sheets of polyaromatic molecules with alkyl and alkylphenol chains, while the archipelago model describes the structure as naphthenic and aromatic components linked together with alkyl or thioether bridges. There is spectrometric evidence for the structures of both models in asphaltenes. The paracondensed and archipelago model are both shown on the left. A third model proposed by Soluble Solutions describes asphaltenes as having high molecular weight and being comprised of multiple large polynuclear aromatic segments held by dispersion or van der Waals forces instead of hydrogen bonds. The 3 proposed models state that changing certain sera molecules will cause aggregation. Because asphaltenes are defined by solubility, there are multiple factors, which include solvent choice, contact time, and solvent-to-oil ratio that may affect which molecules would be found in the asphaltene fraction. To minimize interference from these factors, asphaltene tests should be run for at least 8 hours and a solvent-to-oil ratio of at least 60:1 is used. Using a solvent with a low carbon number may result in a lighter, less polar asphaltene fraction. One study has found that only some fractions of asphaltenes defined by N-heptane solubility are responsible for poor processability. More specifically, the study found that the crude fractions that were insoluble in N-methyl-2-pyrrolidone were the most unstable. Furthermore, temperature is an important variable when testing for asphaltenes, as it was found that increasing temperature decreases the onset time for precipitation. It has been hypothesized that decreasing viscosity is the prevailing factor.